Today, I'm excited. We're going to talk about eliminating the FEA bottleneck. We've got some folks from Solutions here to talk about their product intact simulation and how that works with nTop. Our two presenters, we've got Alex Gay from nTop, a senior applications engineer. He's going to be covering a quick overview of computational design and speaking to the importance of simulation and kind of this really, really fast meshless simulation that Intact offers and how that fits into the process. And then we've got Neil Goldie-Kamar, who's a product manager at Intact Solutions, who's going to do an overview of their technology and then give you a deeper dive demo into what this looks like into a computational design workflow. So with that said, I am going to now hand it over to Neil, who will do a quick intro to Intact and the technology there. So go ahead, Neil, and share your screen.
All right. Hi, everyone.
Now we got
Thanks. All right. Thank you, Brian. Thanks for the introduction and hosting Intact for the webinar. I'm Neil, product manager at Intact. My background is in engineering simulation with a PhD in mechanical engineering. And today with Alec and I will be presenting computational design in nTop, but more going in deep depth of how Intact can really supercharge computational design. So with that note, let's get started. So first, quick introduction of the company. So for those of you who are not familiar with us, we are Intact Solutions. We spun out of University of Wisconsin-Madison almost 25 years ago. So we have been primarily doing research and advanced research and development activities, especially in the areas of engineering simulation, advanced manufacturing, and generative. In our second generation, we expanded to SDKs where Intact could be deployed behind the scenes and be available for simulation on demand. And now finally, we're in our third generation of technology where we are expanding into the end user applications, bringing integrations to nTop, Rhino, Synera, OnSIP, and so on. In addition, we have our automation suite where PyIntact and headless mode of Intact can be deployed in your custom design workflows. So that's what Intact is. So why Intact simulation in the first place, right? So the meshing bottleneck in FEA, as we are familiar with, like meshing is a critical step in finite element analysis and often the most painful step. And with the advancement on design and especially nTop, the kind of complexities we are generating today is getting harder and harder to mesh these geometries, especially quickly if you want to iterate, which is the promise of computational design, right? And the big reason being these traditional meshes have to really conform to the smallest feature in your design, often requires manual pre-processing and sort of breaks any continuity and automation. So with that, to address that challenge, we have developed a meshless, mesh-free simulation technology using immerse method of moments. And the key difference with traditional mesh-based technology is that instead of trying to mesh the original part with capturing all the details and geometries while meshing, we immerse it into a grid of finite elements. And during runtime, we deal with the meshes where the actual the cells where the geometry intersects. We deal with all the computations at runtime instead of trying to mesh at the very beginning. So essentially, it is pretty much classical FEA. Once you have that blue grid all finally computed, all the stiffness is computed, you do FEA as usual, but then at the end, your results are available on the blue grid. We just project it back on the original geometry. And so the original geometry never changed its format, never got meshed. It just helped us inform how the physics is being captured by the blue grid. So that's in short. If you have more technical questions, we can always answer at the end. So that removes the meshing bottleneck because now we are not meshing the original geometry. But then it also opens up some new avenues that were not available before. So first of all, your simulation grid is now fully independent of the geometry, right? So you can change its coarseness, refine it, very much independent of the geometry. So that provides you a fast course analysis if you would like. On top of that, meshes always sort of work with the CAD representation. It needs a surface to be able to do the meshing, FEA meshing. But once you don't have that requirement, you can basically, if any, take any other representation, and if you're able to compute volume on it, we are able to simulate on it. So, your STLs, implicit, big one in nTop. Um, you can have city data coming from as manufactured designs, or you have G code from planning, and you want to quickly see how the material distribution from the G code affects the performance. Mixing representations, BREP with uh, implicits. So all these use cases are possible once you sort of separate the mesh from the geometry. And then since this is a classical FEA, you can take this new mesh and then solve it with any of the existing solvers, or we have our own solvers as well. All right, so we have that technology, and now we bring that to nTop, and especially because we are able to now using nTop generate really complex, high-performance designs, a lot of thin features, small features, like lattices, ribbing. This can be extremely difficult to mesh, if not impossible sometimes. So that's the whole idea behind our bringing Intact to nTop. The whole plugin is inside nTop. So at this point, let's just jump in a demo to see how it works. All right, that's this one. All right, so we are in nTop now. And once you install Intact and go through the initial setup, our blocks will be natively available within nTop. So you can see different loading conditions and solver blocks are available here. So everything is inside nTop. All right, so let's go through a case study. So we have this very familiar connecting rod, lightweighted through a lattice, and we want to do a quick Intact simulation on this one. So first we'll prepare the input for Intact. Basically, we require you to give us the meshes, the surfaces where the loading conditions are being applied. So these two holes at the bottom are fixed, and this cylindrical surface here has a load on it. So we just make sure that's available for us. Some path and directory for the simulation, for bookkeeping, define your material, and that's about it. That's all the pre-processing, if you will, is needed to run Intact. And then we are in our Intact stress block, which is the block that runs the Intact simulation. So in here you can see some, we use those inputs, the directories where everything is present. And for the geometry, we directly take in the implicit geometry. There's no meshing here. It just takes in the implicit. We do ask for a tolerance at which we want to sort of sample this geometry. So in this case, it's 0.2 millimeter. So that sort of defines the accuracy of your implicit we'll be capturing in the simulation itself. After that, some just typical FEA quantities, what kind of basis you want, linear, quadratic, what resolution you want. So this is the number of active finite element cells, the immerse grid cells. If you don't want to use cells, but let's say you want to capture some feature size, then you can just use cell size. Then we have solver type, again, very standard FEA stuff. We provide the material, and then we provide the boundary conditions. So the boundary conditions are using our blocks. So it just takes the surface mesh where it's fixed, and for vector load, we take the load mesh and specify the magnitude of the load. So it's very standard FEA setup you have to do. And once you have all of that, um, this is a pre-run simulation, so the result is already available, and the result from Intact is inside nTop, fully integrated, natively available here. You can look at the results, play with it. That's available. Let's say you wanted to look at results post-process at some cutouts, cross sections. We provide a stress resample block. So basically, you can resample our immersed grid on a new geometry. So in this case, let's say we wanted to look at how the stresses are at the interface of the lattice and the shell. So we can do that as well. So we just resample on that geometry and we have that available. As you can see, all these are, we're capturing all these stresses individually in the struts. So that's the typical workflow of Intact. I didn't go into the setup detail, just walked you through. It was pretty straightforward. But just to show the power of Intact, now once you are, let's say, doing a design iteration, trying to study how different types of lattices affect your design. In this case, we were using, let me turn this off. In this case, we were using this face-centered cubic um, uh, type of lattice. Let's say we change it to body-centric. So nTop is pretty fast at computing the new lattice. As you can see, it has changed here. And our block is showing that the result is stale now. It's 100,000 resolution, pretty high, not extremely high, but still decent high. And I'll show you how quick Intact is now. Everything is the same. I didn't touch anything in the Intact. I'll just rerun this new simulation. I'll trust this block, and then the simulation has started. So as easy as that, changing design, changing parameters of your design. It's very straightforward to run the simulation on the same, using the same block. This one takes around 30 seconds or so. It's a little bit of wait, but still very fast compared to any other FEA you would be using. Especially there's no meshing, right? So the meshing is part of the this block itself. There's no so the total time, so it's already done actually, 35 seconds. Starting from the original design to getting immersing in the grid, computing all the quantities and solving everything took 35 seconds for around 100,000 resolution. And your results are already available. I can turn this off. As you can see, we are capturing the stresses, the stress distribution of how the grid of the lattice is interacting with the shell, as you can see here. So this is a quick demo of how Intact is integrated inside nTop, how easy it is to set up, and how quickly you can start iterating on your designs once you have the initial setup. Very fast. All right, so we go back to the presentation. So, all right, so the results are very fast, quick, but how accurate is it, right? So we have done extensive benchmarking against standard FEA problems. You benchmark your solvers, but in this case, we are showing you the results of convergence study for this connecting rod. So this is on the left, you see the graphs. The blue is the convergence of the displacement inside Intact. So as you can see, since our mesh is independent of the geometry, we are able to go to pretty coarse resolution, 10,000. The results are not good at that stage, but as you can see, around 200,000 elements, we start to get very close result to the converged values here. This window, the dashed window, shows results from a mesh-based simulation of the same geometry. As you can see, the convergence is very similar, 422, 421, but the time taken for convergence is almost half, 259 seconds versus 434 seconds. So faster at very refined analysis. But let's say you are doing you're in the design stages, early design stages, trying to iterate quickly over different design options. We can reduce the resolution to around 200,000 and start iterating at around 100 seconds and while being pretty close to the converged result. So that's one of the flexibilities that Intact provides, especially in computational design. Stress-wise, so displacements were pretty close, usually less than 1% to mesh-based. Stresses, we are within 5% to mesh-based in regions where there are no hotspots. This is a picture showing what the meshes look like. So this is the converged mesh for mesh-based system, and this is our mesh, the regular grid. Typically, we say for convergence, you require 2 to 3 elements across the struts. and which is the case here. So that's how it compares to traditional FEA. All right. So having said all of that, what happens when the complexity really blows up? So for this example, this ribbed structure here, stiffened, we were able to run a simulation with similar accuracy from mesh paste, which took 3,000 seconds within 500 seconds and got the same maximum displacement convergence results. And this is including all the steps of simulation. Some other extremely complex design, this 10 by 10 by 10 thin wall gyroid lattice, we were unable to mesh on our computer in reasonable time, but with intact our meshless, we are able to do this in hundreds of seconds, couple of almost 2 million nodes. And same with this one, we are able to run in 400 seconds this simulation and get a good result. So this is what is enabled once you don't have to be blocked by meshing. You can rapidly iterate and even simulate some of the things that you were not able to simulate before because meshing was just too much of a bottleneck. All right, so at this stage, I will hand over to Alec, who will go over now the computational design aspect of nTop, and then we'll see how Intact can also supercharge that. So over to you, Alec.
Great. Thanks, Neil. Do you see my screen okay?
Yeah, we do.
Looks good. Awesome. Hey everyone, got a lot of participants here, and I see a lot of questions coming in as well. Just make sure you're throwing those in the Q&A, and we'll get everything answered. Also see a lot of familiar faces, so thanks for joining. On our section here, we're just going to talk about what this enables in terms of nTop. And you saw Neil go through a pretty simple demo, and then iterate, very fast with doing, say, a new build of Lattice. And we're hearing from a lot of customers, and it's not the first time you've heard this, that getting a part designed and to market is one of the biggest pushes from a small business to a large business. And there's a lot of pressure in this process to develop, design, validate, and get something manufactured. And we see this across all of our customer base, whether it's aerospace and defense down to R&D or even things like consumer goods. And this is something that enables us to not have to hop around when we're going through that design process. And what you know is that the bottlenecks today are going to be in how we iterate and how we evolve these parts and start to converge on the ideal solution. And typically, whether in motorsports or aerospace, right, it's starting with that initial design or benchmark. Maybe it's some criteria, and you have a set time to get something through these hoops. And lots of times this really limits you to just one or two iterations, right? And you're leaving a lot of performance, a lot of cost still on the table. And what we want to do with nTop in computational design is try to take advantage of that fast iteration, the ability to create these geometries in nTop, leveraging our implicit. And it's very important because across the board, and here are like three major pillars, right? This is going to be struggles in manual modeling. So even things like, trying to do ribbing structure. In this case, this is actually from a Lockheed engineer doing a pressure bulkhead, trying to add these iso ribbings and make a change. And it's not just one or two clicks or maybe trying to change a cell map like in Lattice or like in nTop. What it becomes is a little game of cat and mouse where sometimes it's just easier to start over with a fresh sketch. And they're spending days doing these basic operations. And this same kind of idea of manual modeling trickles down to areas of like design intent. So if you have a complex spline that you'd like to update because maybe you have a new pressure differential goal, this is, again, a place where oftentimes manipulating these or trying to redraw these is going to result in a CAD tree of, beautiful lights and errors. And we want to make it easy to define variables and constraints and make it so it's like turning a dial to fine tune and automatically update the downstream processes that come into play. And one that's going to kind of hit home today is going to be in advanced physics. And something that's really unique about nTact is that we're able to do these simulations very quickly within nTop. So when you're going from the first iteration to say, your 80% mark, you're converging exceptionally fast. And you're not looking at one or two models, right? We're going through maybe a dozen, 24, 100 different iterations. And it's nice because we're not making a mesh to export. and bring back in, right? We're staying in the tool and we're able to run this just like a custom block, because at the end of the day, this is formatted just like a block, and we'll go over that here in a minute. And this big picture comes around with computational design, and we always categorize this as the build, run, and integrate. And as you're building your workflow, you're defining those requirements, the constraints. Maybe you have engineering data and an objective in mind, and we're able to output the results of those, built computational models to its basic structure. And then as we fine tune, or maybe we start to put guardrails on the manufacturing process, or a weight goal, or a weight savings, or maybe even trying new material. What's unique is that we're able to run and iterate this computational model, and this is something that happens very effectively and seamlessly because it's based on our implicit, and we're not relying on, edge face 32 or CAD face 6. It's one continuous volume, and it makes it so we can scale something extremely well from 1 unit cell to 1,000,000 unit cells. It's just one volumetric equation. And of course, this is very important, and you see it here as we're bringing in tools like Intact, where we're able to integrate with downstream tools. And this could be something like a CAD assembly. Maybe it's a simplified representation. Could also be something like a CAE export if you wanted to do a final validation in a sim tool of choice, or it could be some manufacturing constraints or bringing it straight to an OEM that we partner with. And that's really the idea behind these computational models, is we're creating a process that we can use this engineering know-how and knowledge to generate solutions and do it very quickly. And this is just one idea here around design exploration I want to share with you. And it's the basis of a lot what we do when we need to do multiple iterations and look at how these design parameters are going to affect the end product. And this could be, maybe it's the shell size, maybe this is a beam thickness, maybe this is the material type. We're defining these parameters, and we're making them exposed to the user. So if you're new to nTop or you're a seasoned veteran, right, you have those exposed details that are important to you. And generating these designs is very quickly, very, very easy, right? We're just changing an input. And I know you're going to see this here in a second with Neil when we're trying to change things like strut diameters of a rib structure. And evaluating these is very easy because we can also export all of these things like max displacement. Maybe you want to look at how that affects mass, or maybe you want to see what the different types of custom unit cells you've designed in-house, how those might change over time. Even if they're very complex, right? This is a lot easier to iterate through because of the speed that tools like Intact bring to nTop. And to go over that, if you've never seen it, I know we have some first timers on the call. Typically in nTop, right, we're either bringing in something like an outside geometry from a CAD tool of choice. Maybe it is a watertight mesh, or maybe it's scan data. And then we're using that as our basis to start to generate a design. We can also make those designs fully implicit, right? So if you're not converting to implicit, maybe you want to start sketching from implicits. And that's something that we're working on and always kind of iterating with, because it's even faster. And this is how you get into this refinement loop. And, first you're typically doing something like a mesh. But in this case, because you have the implicit and what Neil was mentioning, we're actually able to take that implicit and use it as its volume to do some of these basic analyses up to advanced analyses. And this is really nice because now we're creating the circle a lot faster to travel. And so far, we haven't seen an example with taking data, the continuous feedback loop, back to the actual project in mind. But we're going to see that here in a second, where we're taking those initial results from maybe those first design changes. And now we're running a new Intact sim, and we're going to use those to feed the design changes and vary parameters more. And just like before, we're exporting this at the end of the day. So what that really enables is that we're doing a lot faster iterations. We're doing a lot more designs within that same amount of time we were working with before. Sure, maybe the initial setup is going to take a little longer, but what that builds out is a process, so that when you're going on to the next family of parts that are similar, or maybe it's next year and you have maybe new motorsports regulations, or you have a new CG mass that you're trying to tailor to, it's just a matter of updating those inputs, and we can rerun that same process. So this is all built on our core nTop tech, and you've seen it before. That's going to be our implicit, our reusable workflows, field-driven design, and finally interoperability. And this is a really nice case of where we're taking all four of these and leveraging them at once. So we're building that implicit. We're leveraging things like custom blocks as well as blocks like what Intact has to leverage Intact Sim. And we're making a nice iterative feedback loop for field-driven design and able to use that in not just nTop, but other simulation tools. So with that said, I know we have a nice little demo coming up to show this off. I'll pass it over to Neil and make sure to keep asking questions in the Q&A box. Thanks, guys.
So yeah, let's look at the demo that Alec was talking about to see how computational design with Intact in the loop can really shine. So let's go to the demo. Right. Let me hide this one. Yeah. So in this demo, we have a panel which we want to lightweight coming from, let's say, aerospace. And let's say we have identified that there is a region we can cut out and maybe replace with some ribbing structure while not too much degradation in the performance, while having a good weight saving. So in order to do that study, let's just walk through this workflow. It's already set up. I'll just highlight the simulation part of it as well as the driving the design with the simulation part of it. So the first step would be to prepare again Intact. So we want to have all the faces where your loads and restraints will be applied, set up the Intact, and then we run an initial simulation on the original design. This is what it looks like. Pretty straightforward, same block as we saw earlier. All right, so now we want to start lightweighting it, right? So we go through the awesome capability of generating these ribbing structure. So these are the details of it, but at high level, we are using triangular honeycomb lattice ribbing structure with a rib thickness of 1 millimeter. So this is what the uniform thickness ribs look like. And thanks to the magic of implicits, you can nicely integrate the two, combine the two into this new structure, which should be lightweight without with too much loss in performance. So now we come back to Intact. So we just take in that uniform rib geometry as implicit, as Alec was mentioning, give a geometric tolerance of what accuracy we want to capture that geometry at, run a simulation at 100,000 resolution, and apply the same boundary conditions of pressure and fixed boundary conditions. So I won't go into the FEA details here. And I have a pre-computed result here for you. So you can see this geometry is extremely complex, and meshing this could be, I would say, a real challenge here. A lot of thin features, blended edge corners and edges. So we are able to do that in hundreds of seconds, right? And I'll show you that right now. So let's say we have this initial design, and I noted the numbers. So the original design is at showing a max displacement around 5 millimeter with 161 megapascal of stresses, high stress. And the new design is 15% lighter, but there was slight compromise on the displacement and stress, but still, let's say it's within the design criteria. So let's say now we want to refine this and get more performance out of this design. And we can do that in nTop. So that's the next iteration. So here we want to use the original simulation we did on the original geometry, so the Intact stress. We extract the von Mises stress, right? And the idea here is that we are trying to move more material where the stresses are high and take material away from where the stresses are low in the rib structure. So we bring in the stresses, the original stresses, and then we create a mapping from the min and max of the stress to what thickness variation you want in your ribbing pattern. So in this case, we went with a minimum of 0.25 and a maximum of 2 millimeter thickness. So the max stress, whatever regions where you'll have max stress of 2 will get mapped to 2 millimeter thick ribs, for example. And again, this is the power of nTop here. You take those results and directly map it onto the thickness variable, and we get this variable thickness lattice structure very easily. And again, you take that and combine it with the original design, and now we have a variable lattice design. You can see it added more thickness in this region where the stress was high and took away material in the ribs where the stresses were low. All right, so we have this new design now, and we want to quickly see how this performs compared to the original design, right? So now I will show you how easy it will be to iterate like this with Intact. So let's do the whole workflow. So I go to the original, the workflow where we ran the uniform ribs simulation. I copy it. I bring it over and paste it where our new design is sitting now. Let's call this one from uniform to variable study. And I replace the uniform lattice with variable thickness ribs. So that's it. Everything else, the boundary conditions, the faces did not move, anything did not change. So everything remains constant, only the design changed. So as the setup is as easy. And then I'll run the simulation for 100,000. This is extremely complex geometry. It probably take more than a minute, but still fast enough that yeah, I am doing it live, right? So I started. So this will take a minute. If there are questions, I can take questions.
Yeah, I have
Brian.
a few questions
Yeah,
here,
yeah,
and maybe Brian can add to them.
sure.
But maybe you can talk a little bit about, typically in nTop, we have that steady state linear static analysis. What differentiates, leveraging Intact, and why is it able to do it so fast compared to just like a base solver like nTop has?
Right. So as we saw, right, the meshing is the biggest bottleneck. So once you have that mesh created and the linear system formed, things are very fast. But getting to that mesh is the bottleneck, as we saw. And with Intact, as I showed you in our slide, that meshing bottleneck is removed because we just generate an automated grid and very quickly figure out which geometry, which cells have geometry, what geometry that is, and how that will inform the stiffness of that cell, which is much faster than trying to mesh this part, trying to make sure that the meshes conform to the geometry, the corners, the blendeds. So that's where the sort of the savings come.
No, that's super helpful, Neil. And I know that was asked a few times here early on. So hopefully you guys are getting a picture of that. Um, let's see how this is chugging along here.
All right.
The other one I had, is it done already?
Yeah,
Oh, that was
it's
quick. All
done.
right.
Yeah, 85
This
seconds.
is this is a good problem to have, guys.
All right, I'll turn this off and we have the new variable lattice design. As you can see, the thickness here is higher, lower. You can look at the stresses, and you can see the stresses in individual rib members. And I have the results sort of brought in here already for nice comparison. So this design was much lighter than the second one, so further reduced weight by 5%, so 20% lighter, while we maintain the max displacement and also reduce the stress because we moved material where the stresses were high. So basically, very quickly we were able to improve this design, and the more advanced designers can really push this forward and really get complex design, more performant design rapidly. All right. So that was the demo. I'll quickly wrap up with some examples. So Alec already showed about this one, the scatter plot, but this is the design Gabby at nTop did. 256 simulations, high fidelity simulations, 2 minutes each, and sweeping the ribbing patterns for different parameters very easily. And you can generate all the studies and then fine tune which areas you want to study more or refine at. Lattices, no problem. This was a fast simulation study. We were doing at low resolution. We were able to do 124 simulations in 2 hours. Again, multiple parameters spanning cell sizes and type of lattices and thicknesses. Very quick to do these analysis. And on that note, yeah, that was Intact simulation. So this it is currently available for trial. You can download it and try it out for 2 weeks. Just to reiterate, no meshing bottleneck. Directly work with the implicit model without having to generate a surface mesh for it, for example. It's fully automated and integrated within your nTop workflow, so you don't have to leave nTop. You can just stay in your design context and iterate rapidly. And we saw we can do both fast analysis for initial design phases and refined analysis. Yeah. So on that note, yeah, I think I'm done on my end, Brian.
Awesome. Thank you, Neil. That was great. Just want to thank everyone for joining today. I want to thank Alec and Neil for presenting an amazing job, and also Rick for being here to help answer questions at the end. So thank you all. We'll wrap up the webinar now. If you have any additional questions, feel free to reach out to us after the fact, and we'll go from there. Thank you, guys.
Right. Find us on LinkedIn, find us emails. Yeah, we're everywhere. So we'll answer your questions.
Thank you, Brian.
Thank you, Brian. Yes.
Yeah.
And Alec.
Thanks, everyone.
Alec,
Yeah.
yeah.
Bye.
Bye.
Cheers.